Okay, so we're coming to this part that talks about types of solids. Okay, so one important thing that you see here is there are two main categories of solids. One is called crystalline and another one is called amorphous. Okay, so what is the difference? Now, if you look at this structure here, this is a simplified structure. I want you to notice that every layer of atoms here is arranged in a regular fashion, one above the other. And there is very little gap that you see between them. Okay, so that means they are packed very tightly together. So this is crystalline type of structure. So crystal, so they're very hard. Okay, they are very hard. If you hit them really hard, they will shatter. They don't just go into powder, but they shatter. Quartz is an example, like sand is an example. Amorphous solids do not have much structure, much order. So look over here. They are solids. Most of their atoms are touching each other. Most of them are. But then you find some gaps in between them. All right, there are some gaps. And this allows the atoms or the molecules to move. For example, if you apply a force over here, let's say you apply a force over here, this entire structure can collapse into this space. Or if you apply force over here, this entire structure can collapse into this space. So this is called amorphous. They are solids. You look at them, they are solids, but in actual fact, they are soft solids. Okay, they're soft solids. So plastic bags are an example. Okay, so this is just an example of the types of solids. So we have crystalline and we have amorphous. Now, crystalline solids can be classified as for example, they can be classified as ionic, metallic, covalent network, and covalent molecular. Okay, ionic, metallic, covalent network, and covalent molecular. So if you look at this next table here, you will notice that those which are ionic, metallic, you look at the melting points and boiling points, right? They are really high. High meaning, compared to 30-40 degrees, 100 degrees water boiling, these are in their thousands. So these three guys, ionic, metallic, and covalent network, they have very high, except for mercury if you see them, because mercury is the only metal which is liquid at room temperature. So, but the rest of them, look at the temperatures are really high. Their melting temperatures are in the hundreds, and their boiling temperatures are in the thousands. Okay, so these crystalline structures have very strong, their atoms or the particles that make them up have very strong attraction to each other. That is why they have very high melting and boiling points. Meanwhile, molecular covalent, basically these are molecules, okay, simple molecules like hydrogen, iodine, water, ammonia, chlorine, bromine, iodine. Generally, if you see their metallic melting points and their boiling points are relatively lower than the rest just now. So ionic, metallic, covalent network, they are more crystalline types of structures, meaning their atoms or the molecules or the ions that make them up are very tightly held together. Okay, so very quickly we'll just go through this properties of ionic solids. They have high melting points, okay, because ionic bonds are very strong. Okay, they do not conduct electricity in solids state because the ions need to be free moving. So you need to have the positive and negative ions to be free moving for them to be able to conduct electricity. Ionic compounds, crystals are solid, are hard, but they are brittle. So this almost sounds like it's contradictory. Hard but brittle. Now, brittle is when a force is applied in a certain way and it causes the solid to break apart. Okay, you see here. So if you look at this example over here, in any ionic solid, right, every negative ion is surrounded by positive ions. Okay, and every positive ion is then surrounded by negative ions, if you see over here. All right, so every positive surrounded by negative, every negative surrounded by positive. That keeps them together. But when you take a hammer and you apply a force for maybe for a millisecond, for even for a very short period, when you apply the force, the layers can collapse. Just maybe they just collapse a little bit. And then suddenly charges of similar, ions with similar charges come face to face. When they come face to face, what happens is there will be repulsion. So what will happen is there will be repulsion at this point, because ions of the same charges come face to face. And at this very moment, there will be a crack. Like glass cracks, ionic compounds crack as well. That is why we call them brittle. Okay, we call them brittle. So when you hit a hammer, if it's hard enough, the layers will slide and ions with similar charges come face to face. All right. Okay, so that's that. Now, metallic solids are the best because metallic bonding is very, very flexible. Okay, metallic bonding is very flexible, and we looked at this earlier in the earlier chapters. Okay, but it's very flexible, and they are good conductors of electricity. They have high density, which means that the atoms are all very tightly packed together. And one important criteria of metals is they are ductile and they are malleable. Ductile and malleable. Now, ductile basically means they can be pulled to become long wires. Malleable meaning they can be beaten and they can be changed into different shapes. So basically, if you have, let's say, a layer of atoms of metals, right? Let's say this is one layer, then this is another layer of atoms of metals. All right, let me just try to do this. Okay, so let's draw 4 layers of atoms here. 4 layers. So when a force is applied, let's say you apply a force over here, right? When you apply a force over here, what happens is this layer, this top layer here, can actually slide. It can slide over the other layers. They can slide. And when they slide, they can slide and collapse here and then continue. So this suddenly becomes a long wire, you see? So they can actually slide. This is called ductility. They are able to be pulled into wires, all right? When we talk about malleability, let's say if you apply a force, over here, what happens is the layers of atoms can rearrange themselves so that, they bend, right? So let's say they bend, so they create a little gap here, and then the other layers just go and stick at the top there like that. So they bend in. So this whole layer has gone inwards. So that's malleability. All of these things happen because metallic bonding is very, very strong, and it is made up of delocalized electron systems. That means metallic bonding doesn't go from point A to point B. It doesn't go just this way. It is in all directions. Metallic bondings exist in every direction. That is why it's called non-directional. So it's very strong. That makes it malleable and ductile. Okay, so covalent network. Now, covalent network, when we talk about covalent network, we are talking about 2 very important things. One is those which are like diamond. You see, like if you look at the structures here, right? Okay, not very clear here. You see, like diamond, what happens is every single atom in diamond, every carbon is attached to another 4 carbon atoms. All right, another 4 carbon atoms. And in return, this carbon is then attached to another 4 carbon atoms, which this was then attached to another 4 carbon atoms. And then it just goes on and on and on. So this was probably attached to another carbon here, which was attached to another carbon and another carbon. And this structure just goes on and on and on and on and on. Okay, it's non-stop. So every carbon atom is bonded to other carbon atoms via very strong covalent bond. Same thing goes with when we talk about, let's say we talk about silicon dioxide. In silicon dioxide's case, every silicon is attached to 4 oxygen atoms. Okay, every silicon is attached to 4 oxygen atoms. All right, so there's another silicon here attached to 4 oxygen atoms. So let's say there's a silicon here attached there, it's oxygen. So every atom is bonded to another atom via covalent bonds. So this is why network structures are very, very hard. Compared to even metallic and ionic compounds, network structures have high melting points and high boiling points, okay? Because what is holding them together is 100% covalent bonds. All right. So then brings us to molecular solids. Molecular solids are the weakest of them all. Now, in the case of molecular solids, right, these are all examples of molecular solids, right? So when you say molecular solids, like for example, like in the case of fluorine, fluorine is made up of two atoms. And that's it. This is one molecule of fluorine. And then there's another fluorine, another molecule. Then another fluorine and another molecule. The attraction that exists between each of these molecules, this is what we call secondary bonding. This secondary bonding is very, very weak, okay? And you notice another thing, when you're going from fluorine to iodine, the melting point increases and the boiling point is increasing, because this secondary bonding, the strength of the secondary bonding depends on molar mass. So as the molar mass increases, okay, so as the molar mass increases, secondary bonding also increases. Secondary bonding also increases. So which means that their melting points, boiling points will increase. But because it is very weak compared to the others, their melting points and boiling points are relatively lower. Okay, same thing with noble gases. Noble gases also same thing. Although they are only made up of a single atom, the attraction that exists between them, okay, the attraction that exists between the, so let's say if this was neon, let's say this was neon, the attraction that exists between them, this secondary bonding is very, very weak. Okay, it's very, very weak. And again, the same concept, as you go from here, the molar mass is increasing. As the molar mass increases, the secondary bonding is also increasing, the strength increases, so the melting point, boiling points will increase. Okay, so that will bring us to the next part, metals and alloys. But metals and alloys is not in the syllabus anymore. It's not in the syllabus, so we are not going to be talking about this. We are not going to be talking about alloys. All this is not in the syllabus. All this is not in the syllabus, thank God. That brings us to allotropes of carbon, and this would be in the next video.